I'd like to invite the recipient of the 2017 CNS Resident Award to make a presentation on his research on SIRT1 activation as a neuroprotective agent in subarachnoid hemorrhage. Please join me in welcoming Ananth Vellimana.
Good morning, everybody. I'd like to thank the leadership of the CNS for this opportunity, and I'm going to talk about some work that I did in the laboratory of my mentor, Dr. Greg Zipfel, at WashU in St. Louis. The topic is SIRT1 activation, a strategy for harnessing endogenous protection against subarachnoid hemorrhage-induced neurovascular dysfunction. We have no financial conflicts of interest. This work was funded by grants from the NIH as well as the NREF. As all of you in the audience know, subarachnoid hemorrhage is associated with significant morbidity, and a good proportion of survivors have long-term deficits. And over the last few decades, multiple trials have tried to improve outcome in patients with SAH and unfortunately have failed. A major reason for this is that these trials were directed primarily against improvement of vasospasm with the expectation that it would improve outcome. New research over the last decade or so has shown that outcome after subarachnoid hemorrhage is affected not only by vasospasm, but there are multiple other components. As you can see here, secondary brain injury is divided into two components, early brain injury as well as delayed cerebral ischemia. And vasospasm continues to be the primary driver of delayed cerebral ischemia, but is not the sole contributor. And ultimately, a combination of these factors are what leads to poor outcome. And so future therapeutic strategies directed against multiple components of secondary brain injury are needed to improve outcome in SAH patients. And this leads us to the concept of endogenous neurovascular protection. And conditioning, which is how we do our experiments, is a phenomenon where exposure to sublethal quantities of a normally injurious stimulus can enhance or reduce the severity of subsequent injury and enhance reparative processes. In other words, what does not kill him makes him stronger. And so the protective phenotype induced by a conditioning stimulus is due to its effects on all neurons, glia, as well as the vasculature. And we believe that SAH is an ideal condition for a conditioning approach because there's a high incidence of secondary brain injury after SAH, and the injury that occurs is multifactorial and is due to effects on neurons, glia, as well as the vasculature. And there is a window of opportunity between the ictus and the onset of secondary brain injury. And so our work started several years ago with a proof of concept experiment. In that study, as well as subsequent studies, we used adult mice, and subarachnoid hemorrhage was induced by endovascular perforation, and we did a battery of neurobehavioral tests as well as assessment of vasospasm and microthrombosis. And so in the initial proof of concept experiment, the conditioning stimulus that we used was hypoxia, which was 8% oxygen for 4 hours, administered prior to SAH, followed by hemorrhage and then multiple assessments. And we found that conditioning induces a robust protection against vasospasm and deficits. And I won't go into further details, but through multiple experiments, we demonstrated that this was mediated by endothelial nitric oxide synthase. So again, just to recap, preconditioning provides strong protection, and this protection is mediated by eNOS. In order to translate this approach, there were two issues. First, we need a conditioning strategy to be applied after SAH. And the next is since hypoxia cannot be administered in a clinical setting, we need to identify a molecular initiator of this conditioning-induced protection. So for the first part, our first attempt was to use the same stimulus that we used for our preconditioning experiments, that is 8% oxygen for 4 hours. Unfortunately, that led to significant mortality and was not effective. So then we reduced the severity of our stimulus and used 8% for 2 hours and also tried 11% for 1 hour, which is an even milder stimulus. And we found that the moderate repetitive hypoxic conditioning with 8% for 2 hours protected against vasospasm, also protected against microthrombi, and ultimately improved neurological outcome. And so now that we've demonstrated that a conditioning strategy works after SAH, the next step was to identify a molecular initiator that could be ultimately pharmacologically targeted. And the expected characteristics of such a molecule would be that it's responsive to hypoxia and is related or regulates eNOS. And so we screened a few candidates and ultimately honed in on SIRT1 or SIRT2-in-1, which is an NAD-dependent protein deacetylase. And we chose that because it was hypoxia responsive, had been shown to upregulate eNOS, and was implicated in neuronal protection induced by conditioning. And in our hands, we found that hypoxic conditioning increased the expression of both mRNA as well as protein levels of SIRT1. And when we gave EX527, which was a SIRT1 inhibitor, we saw that the preconditioning induced protection, which you can see in the red box, was lost. Similarly, neurological protection was also lost. I have additional data with microthrombi and other components, which I'm not showing for lack of time. And then similarly, we used the inhibitor in post-conditioning as well. And again, the post-conditioning induced protection that you can see in the red box was lost with SIRT1 inhibition. So these suggested, again, same thing with neurological deficits as well. So these experiments suggested that SIRT1 is critical for the conditioning induced protection that we saw. And then we tried to mimic this by using mice that transgenically overexpress SIRT1. And we saw that while wild-type mice on your left-hand side had significant spasm and deficits, which you'll see in the next slide, transgenic mice overexpressing SIRT1 were protected from vasospasm deficits and also microthrombi, etc., which I'm not showing here. We basically demonstrated that the protection induced by conditioning is dependent on SIRT1. So the next step was to use a pharmacological activator to see if we can mimic conditioning-induced protection. So we chose resveratrol, which is a component of red wine and is known to reduce vascular dysfunction, reduce oxidative stress, inflammation, among other functions. And we saw that administration of SIRT1 increases, or resveratrol increases SIRT1 levels and improves endothelium-dependent vasodilation. And then when mice were administered SIRT1, there was a dose-dependent protection against vasospasm, and this protection was lost with EX527, which is a SIRT1 inhibitor. Again, you'll see similar results with neurological deficits as well. So this suggests that resveratrol tended to mimic conditioning-related effect in a SIRT1-dependent manner. And again, similarly, we performed analogous experiments with to mimic post-conditioning. And so when mice were administered resveratrol after SAH, a similar protection in vasospasm against vasospasm was seen, and this was lost with SIRT1 inhibition. And similarly, neurological protection that was seen with resveratrol administration was again seen and lost with SIRT1 inhibition. We have additional data with microthrombi as well, which I'm not showing for the lack of time. But to conclude, hypoxic pre- and post-conditioning induced a powerful response and protection against vasospasm, microvascular dysfunction, as well as neurological deficits after subarachnoid hemorrhage. And this protection that is seen both pre and post is critically dependent on SIRT1, and that SIRT1 activation could mimic conditioning-induced protection. So this led us to conclude that SIRT1 activation is a promising novel therapeutic strategy to combat the dysfunction after aneurysmal subarachnoid hemorrhage. And so at this moment, our lab is testing resveratrol as well as other proprietary SIRT1 activators, and ultimate hope is for a translational study. And I'd like to thank Dr. Ziffel and members of the lab for all their assistance with this. Thank you.